Welcome all. So here we discuss Schanuel's lemma. First I will state this lemma and then I will say what is the use of this lemma, and then at the end I will give the proof of this lemma. So here is the statement. So you consider an R module M, and suppose you have projective R modules P and P prime, and from P to M you have surjective module homomorphism, that is phi, and from P prime to M you have surjective module homomorphism, that is psi. So you can extend this surjective module homomorphism to a short exact sequence like this. So basically, suppose you have two short exact sequences like this, and this is fixed R module M, and both P and P prime, these are projective R modules. So in this situation, this lemma says that we have an isomorphism like this. So P direct sum K prime, it is isomorphic to P prime direct sum K. And dually we have this statement. So here you consider an R module M, and suppose you have two injective R modules Q and Q prime, such that from M to Q you have an injective module homomorphism, let us say phi, and from M to Q prime you have injective module homomorphism, let us say psi. So then you can extend this thing to a short exact sequence like this. So you can take just co-kernel of phi. So you have a short exact sequence like this, where this is fixed R module M, and Q prime both are injective R modules. So in this situation, this lemma, it says that we have isomorphism like this. So Q direct sum L prime, it is isomorphic to Q prime direct sum L. So let's see that how we can use this lemma. So it says that using this lemma we can have uniqueness of the syzygy modules of a module up to free summers. So first let me say what is the syzygy modules of a module. So you consider an R module M, then we have proved that any R module, it is quotient of a free R module, and hence quotient of a projective R module. So in other words, for any R module M, you can have a free R module F, such that from that free R module to M you have a surjective module homomorphism. So you can extend this surjective module homomorphism to a short exact sequence just by considering the kernel of phi. So then kernel of phi, we call it syzygy module for this surjective module homomorphism. But here this free R module, it is not unique. So for example, we can have another free R module F prime, and from that free R module F prime to M we can have another surjective module homomorphism. So for this surjective module homomorphism, if we consider kernel of that, then it is a syzygy module with respect to this surjective module homomorphism. So then using this lemma we can have a relation between these two, and hence we can have a relation between syzygy modules. So we can say that syzygy modules are unique up to a free summon. So here kernel of phi direct sum this free R module F prime, it is isomorphic to kernel of phi prime direct sum this free R module F. And similarly we can have this statement. So it says that uniqueness of co-syzygy modules of a module up to injective summons. So what is co-syzygy modules? So for injective modules we have proved that you consider any R module M, then it is a submodule of some injective R module. So in other words, you can have injective R module Q such that from M to Q you have injective module homomorphism. So if we denote this thing by phi, then we can take the co-kernel of phi, and then this will give a short exact sequence. So this co-kernel we call it co-syzygy module. Okay, and so of course here also this injective R module, it is not unique. So for example, you may have another injective R module Q prime, and for that you can consider so let us say it is psi, and you can consider co-kernel of psi. So then this will be the co-syzygy module with respect to this injective module homomorphism. Then because of this lemma, we can have a relation between these two co-syzygy modules. It is saying that this direct sum, this injective module, it will be isomorphic to this direct sum with this injective R module. So co-syzygy modules are unique. So this we call first co-syzygy module of M. So co-syzygy module of any module, it is unique up to injective summands. So in this way we can construct free resolutions, and by considering co-syzygy modules we can consider injective resolutions. So because of this lemma we can have relations between any two projective resolutions or free resolutions and any two injective resolutions. And next we will prove this lemma. So to prove this lemma we use push out and pull back of two module homomorphisms. So let me first discuss this notion. So here you consider, so suppose you have three R modules, let us say L, M and N, and from L to M you have a module homomorphism, let us say it is phi, and from L to N you have module homomorphism, let us say it is psi. And then this lemma it says that we can have an R module W such that along with two module homomorphisms from M to W, that is alpha, and from N to W, that is beta, such that this diagram is commutative. And that R module we call it push out of these two module homomorphisms. So let us see how we can construct such R module and these module homomorphisms. Okay. So here is the way. So first you consider this direct sum M direct sum N, this is an R module, and then you consider this collection of elements in this direct sum. What is that? So for each element in L you just consider phi of x, first component is phi of x and second component is minus psi of x. So then this is a subset of this, and then one can verify that it contains the 0 element, namely if you take x equal to 0, then it is 0 comma 0, it is so 0 element is there, it is non-empty subset of this, and you can prove that this subset it is closed under addition and scalar multiplication. So you consider any two elements here and you add them, since both phi and psi are module homomorphisms. So you can prove that this subset it is closed under addition and scalar multiplication. So therefore this is a sum module of this direct sum. So we can consider this quotient module, and we consider this quotient module as W. So this is our R module, and next we should find these module homomorphisms so that this diagram is commutative. Okay. So we have this W, and then how to give a map from M to W in a natural way. So we can see that from M to M direct sum N we have natural map, namely it is mapping y to y comma 0, and then from this M direct sum N to modulo V, this quotient module, we can just map this element to its equivalence class. So modulo, so this is equivalence class of y comma 0 modulo this sum module V. So just by taking composition of these two maps we can have a map from M to W. So this is our alpha, and in similar way we can define map from N to this from N to W. So it is just Z is going to 0 comma Z whole bar. So then we can verify that this diagram is commutative. So you come this way, it is same as coming this way. So how to verify that? So here you consider an element in L. So this is an element in L. So then if you apply phi, then it is phi of x, and then if you apply this vertical map, it is so what is alpha? So this is our alpha. So alpha is mapping, so it is just phi of x comma 0, its bar. And then if we use this vertical map, so this is psi, so it is psi of x, and what is the image of this horizontal map? Beta. So beta is defined in this way. So beta is mapping z to 0 comma z, its equivalence class. So here we get 0 comma psi of x and its equivalence class. So now question is, to prove this diagram commutative, we need to verify that these two elements, this equivalence class, that should be same as this equivalent class. So are they equal? That is the question. So yes, these are equal because of the construction of W. So in W we can, so if we consider phi of x minus psi of x, so this is an element in V, and W is just quotient module of m direct sum n modulo V. So if we consider its equivalence class, so this is 0 in W. So and since this is 0, so we can have that this equivalence class, it is same as this equivalence class. So we have that this diagram is commutative. Okay. And then so this R module W along with this module homomorphisms alpha and beta, we call push out of these two module homomorphisms phi and psi, or we call fiber sum of phi and psi. And here is some property of this W. So it is saying that if this map is injective, then this beta, that is also injective module homomorphism. And if this psi is injective module homomorphism, then this alpha, that is also injective module homomorphism. So let us just verify at least one statement here. So we need to prove that, so suppose phi is injective, we need to prove that beta is injective. So what is beta? So beta is mapping any element z to its equivalence class of 0 comma z. So suppose this equivalence class is 0 element in W. So therefore this 0 comma z, that should be an element of V, and therefore 0 comma z, so we can write it as phi of x comma minus psi of x, it's so for some x belongs to L. And since we have equality, so first component that should be same as 0. So therefore phi of x, that is 0, and then we can use that phi is injective, so x is 0. And once x is 0, then we can see that then z, that is the second component of this element, that should be same as this. So z is minus psi of x, and since x is 0, so minus psi of x, that should be 0. So therefore z, that should be 0. So if z is going to 0 element here, then that z should be 0. So it is basically proving that kernel of, so if kernel of phi, that is trivial, then kernel of beta, that is also trivial. So phi is injective, that implies beta is injective. And in similar way, you can prove that psi is injective, that implies alpha is injective. We will use these properties later. And here it is the dual notion of push out. So it is saying that suppose you have 3 R modules, let us say M, N and Y, and from M to Y you have a module homomorphism, let us say phi, and from N to Y you have module homomorphism, let us say psi. So then this is this lemma, it says that you can have an R module X along with these module homomorphisms pi 1 and pi 2 from x to m and from x to n. such that this diagram is commutative. So, how to construct such R module? And such R module along with this module homomorphisms, so that this diagram is commutative, we call such R module as pullback of these two module homomorphisms, okay, or we call fiber product of these two module homomorphisms. So, here is the way to construct this R module X. So, first we consider, so this is also some subset of M direct sum n. So, in this case we just collection of all those tuples where first component is coming from M, second component is coming from n, such that we have this equality. So, phi of A that is same as psi of B. So, because we want to construct an R module along with this module homomorphism such that this diagram is commutative. So, therefore, we are considering this collection. And now one can verify. So, this is again this is a subset of this, and one can verify that it contains the 0 element, so 0, 0 that tuple, and also this subset it is closed under addition and scalar multiplication. So, because phi and psi both are module homomorphisms, so using that one can verify that this is a submodule of this direct sum. So, this is our X, and next we want to we want to find this module homomorphisms phi 1 and phi 2. So, since this is submodule of this direct sum, so from M direct sum n to M we already have this projection map, projection on the first component. So, namely it is mapping x comma y to x. Then if we take restriction of this map phi 1 on this submodule, then that is also giving a module homomorphism. So, restriction map of a module homomorphism, it gives another module homomorphism. So, this is our phi 1. So, phi 1 is the restriction map of the projection map on the first component, and this is the restriction of the projection map on the second component. So, next we should verify that this diagram is commutative. So, we can do that here. So, here you consider an element x comma y, this is an element in x. So, therefore, it is so x comma y, this is an element in this direct sum such that we have this equality. So, then if we apply phi 1 on x comma y, we will get x here, and if we get phi 2 on x comma y, we will get y here. So, if we apply this horizontal map psi, then it is just psi of y, and if we apply this vertical map phi, so it is phi of x. So, now question is, are they equal? Answer is yes, because of the construction of x. So, this is an element of x, therefore, we have equality that phi of. So, this R module x along with this module homomorphisms we call pullback or fiber product of these two module homomorphisms. And here is the property of pullback. So, it is saying that if this map phi is surjective, then that implies that this vertical map that is also surjective module homomorphism. If this psi is surjective module homomorphism, then this phi 1 that is also surjective module homomorphism. So, let us prove this statement. So, suppose phi is surjective, we want to prove that phi 2 that is surjective. So, you consider an element in the codomain of phi 2 that is B, and we want to find something here. So, we want to find some pre-image of B. So, starting from B we can come this way. So, this is just psi. So, it is psi of B, and then we can use the hypothesis that this phi that is surjective. So, we should have a pre-image here. So, let us say it is something, let us say it is x, some element whose image via this module homomorphism phi that is psi of B. So, then we can just we can just consider this element. So, if we consider x comma b, then we can see that its image is x. So, and so that should be the pre-image, that should be the pre-image of b, because so this is just projection map on the second component. So, x comma v, it is going to be, and this is an element of x. Why? Because this x it is a pre-image of psi of b. So, if we apply phi on x, that is same as psi of b, we have this equality. So, therefore, x comma v, this is an element of x and its image is b. So, using the fact that phi is surjective, we can prove that this phi 2, that is also surjective, and in similar way one can prove that if psi is surjective, then phi 1 is surjective. We will use that to prove. So, you consider these two short exact sequences, and where p and p prime, these are projective R modules, and you have fixed R module M here. So, we need to prove this isomorphism. So, here we consider these two short exact sequences. Therefore, we have these two module homomorphisms, phi and psi. So, phi is a module homomorphism from p to m, and psi is a module homomorphism from p prime to m. So, we consider these two module homomorphisms, and then we can consider its pullback. So, suppose x is the pullback of these two module homomorphisms along with these module homomorphisms. And then we have already proved that if this map is surjective, then pi 2, that is surjective, and if this psi is surjective, then pi 1 is surjective. So, in the hypothesis, so we started with these short exact sequences. So, therefore, this map phi and psi both are surjective module homomorphisms. Hence, pi 1 and pi 2, these are surjective module homomorphisms. So, considering pi 1 and pi 2, we can construct another short exact sequences like this. So, this pi 1, it is surjective, and pi 1 is a map from x to p. So, if we consider the kernel of pi 1, then it is giving a short exact sequence. So, here this is the inclusion map, and similar way considering pi 2, we have this short exact sequence. Now, we should use the hypothesis that both p and p prime, these are projective R modules. So, one of the equivalent condition we have that if a short exact sequence ending with a projective R module, then that is a split short exact sequence. So, therefore, this middle one, it should be isomorphic to p direct sum kernel phi 1, and for the same reason, since p prime is projective R module, we have this isomorphism. So, this middle one x, it is isomorphic to p prime direct sum with kernel pi 2. So, we have these two isomorphisms, and then so we want to prove this isomorphism. So, we have these two isomorphisms. So, from here we can see that this is isomorphic to this. So, once we prove that kernel pi 1, it is isomorphic to k prime, and kernel pi 2, it is isomorphic to k, then we are done. Then we have this isomorphism. So, let us prove this isomorphism now. So, here we write kernel of pi 1, because kernel of pi 1, it is just sum module of x, and we should prove that kernel of pi 1, it is isomorphic to k prime. But if we consider this short exact sequence, then from here what we get, that k prime, it is isomorphic to its image via this map, and since this is short exact sequence, so image of this map, it is same as kernel of this map. So, basically we are getting that k prime, it is isomorphic to kernel of psi. So, if we write kernel of psi here, then k prime, it is isomorphic to this kernel of psi, and kernel of psi, it is already sitting inside p prime. So, it is just content kernel of psi, it is contained in p prime, and we have this module homomorphisms from x to p. and this is a submodule of X, and this is a submodule of P prime. So, if we just consider the restriction map here, restriction of pi 2 on this, then I claim that that restriction map will be isomorphism. So, here I should write that this is the restriction map. So, this is pi 2 restricted on kernel of pi 1. So, if you consider any element in kernel of pi 1, so it looks like some element of x a comma v which is there in kernel of pi 1. So, kernel of pi 1, so pi 1 it is just mapping a comma b, it is just mapping to a. So, if a comma b is there in the kernel of pi 1, that means this a that should be 0. So, any element in kernel of pi 1 it looks like 0 comma b. And then if we apply this restriction map pi 2, then its image is b. So, this is the map from kernel phi 1 to kernel psi, and we need to verify that this map it is isomorphism. So, is it injective? Answer is yes, because any element in kernel phi 1 it looks like this, and suppose it is going to 0 via this map. So, therefore, b is 0, and once b is 0, then this element is 0. So, kernel of this map it is trivial. And is this map surjective? Answer is yes, because if we consider an element in kernel of psi, so element of kernel of psi, so suppose b it is an element of kernel of psi. So, therefore, b it is going to psi of b, and that is 0. It is, we can think that this is the same as phi of 0. So, therefore, we can just consider this element 0 comma b. So, this since phi of 0 it is same as psi of b. So, this is an element in X. So, this 0 comma b it is an element of X. So, for each element b in kernel of psi we are getting a pre-image here in X. So, therefore, this map it is also surjective. So, it is injective and surjective. So, this is isomorphism. So, kernel of pi 1 it is isomorphic to kernel of psi, and kernel of psi it is isomorphic to k prime because of this short exact sequence. So, therefore, we have this isomorphism, and in similar way we can prove that kernel of pi 2 it is isomorphic to k, and hence we have so this is isomorphic to this, and using this isomorphism we can have this isomorphism, and that is the proof of Schanuel's lemma for projective modules. And here is the Schanuel's lemma for injective modules. So, again let me recall the statement. So, you consider an R module M, and suppose you have two injective R modules Q and Q prime, and from M to Q you have injective module homomorphism. So, you have this short exact sequence. So, these two short exact sequences where this middle one Q and Q prime are injective modules, then you can have this isomorphism. So, to prove this lemma, in this case we use push out of these two maps. So, considering these two short exact sequences, we can consider these two module homomorphisms phi and psi. So, phi is a module homomorphism from M to Q, and psi is a module homomorphism from M to Q prime. So, then we can consider push out of these two module homomorphisms. Let us say it is W along with these two module homomorphisms alpha and beta. And if we recall the construction, how to get W? It is just quotient module of these two direct sum of these two modules Q and Q prime modulo V. So, V is given by this thing. And then we have also verified that if phi and psi are injective module homomorphisms, then that imply that alpha and beta, these are also injective module homomorphisms. So, this alpha, this is injective module homomorphism from Q to W. So, considering this injective module homomorphism, we can have a short exact sequence like this, and considering this injective module homomorphism, we can have a short exact sequence like this. So, just we have to consider co-kernel of beta. So, then we can use the fact that both Q and Q prime, these are injective R modules. So, one of the equivalent condition was that any short exact sequence starting with an injective R module, that is a split short exact sequence. So, since Q is injective R module, this is a split short exact sequence, therefore, this middle one, it is isomorphic to Q direct sum co-kernel of alpha. And for the same reason, since this is injective R module, we have this isomorphism. This middle one, it is isomorphic to Q prime direct sum co-kernel beta. Now, again, once we prove that co-kernel alpha, it is isomorphic to L prime, and co-kernel beta, it is isomorphic to L, then since both are isomorphic to W, so these two are isomorphic, and once we have these two isomorphisms, we can have this isomorphism. So, let us verify at least. So, in this case, we can just use this diagram. So, here we consider co-kernel of phi, and here we consider co-kernel of beta. So, from W to co-kernel of beta, what is co-kernel of beta? It is just W modulo image of beta, and so from Q to co-kernel of phi, we can have this natural projection map. And then we can, so considering this module homomorphism from Q to W, we can have a module homomorphism from co-kernel of phi to co-kernel of beta. So, namely, we can consider an element here, it is equivalence class of some element of, and then its image we just define in this way, just by considering this map alpha. So, if we recall the definition of alpha, what was that? So, it is giving a map from Q to W. So, it is mapping y to y comma 0, its equivalence class. So, y comma 0, this is an element in this direct sum, and if we consider its equivalence class, that is modulo v, then this is an element in W. So, if we consider the image of y bar, it should be equivalence class of y comma 0. So, in this way we can have a map from co-kernel of phi to co-kernel of beta. We will prove that this map, it is isomorphism, and once we prove this is isomorphism, then we can see that co-kernel of phi, it is isomorphic to L. Why? Because we have this short exact sequence, and co-kernel of phi, it is just Q modulo image of phi, and image of phi, it is same as kernel of this map. So, Q modulo kernel of this map, that means Q modulo image of phi, it is isomorphic to L. That is the first isomorphism theorem. So, considering this short exact sequence, we can have that co-kernel of phi, it is isomorphic to L. So, once we prove that this map, it is isomorphism, then we are done. Then we have this isomorphism. So, let us verify this isomorphism. So, first we should prove that it is injective. So, suppose y comma 0 bar. So, this is 0 element in co-kernel of beta, and what is co-kernel of beta? So, it is just W modulo image of beta. So, if something is 0 here, that means this element y comma 0, it is there in image of beta. And again, if we recall the definition of beta, So beta is a map from q prime to w. So it is just mapping z to 0 comma z its bar. So since this is this element, so suppose this element is 0, therefore it is 0 in co-kernel of beta, and hence this y comma 0 that should be there in image of beta. So therefore y comma 0 bar that should be same as 0 comma z bar, because image of beta it looks like this kind of element, this. So if this is 0, then y bar that should be 0, and so thus we have that this module homomorphism it is injective. And next we should verify that this module homomorphism that is also surjective. So we should verify that this this surjective module homomorphism. So we just consider an arbitrary element, let us say y comma z its bar, the equivalence class of y comma z. It is an element here in co-kernel beta. So we need to prove that this arbitrary element it looks like this kind of element. Then only we can say that this is there in the image of this map. Okay. So and that will prove that this map is surjective. So we have considered an arbitrary element in co-kernel of beta, and we should prove that this arbitrary element it looks like this kind of element. So since we are considering, so this is just y comma z bar, and this is an element in this co-kernel beta. So this is image beta, okay, and then we should prove that so I claim that this is same as y comma 0 bar plus image beta. Why? Because if we just take 0 comma z bar out, so 0 comma z bar it is there in image of beta. So therefore this arbitrary element it is just same as equivalence class of y comma 0, because 0 comma z that element it is there in image of beta. So this map it is also surjective. So thus we have isomorphism here, and we have already argued that co-kernel phi it is isomorphic to L because of this short exact sequence. So we have this isomorphism, and in the similar way one can prove that co-kernel of alpha it is isomorphic to L prime. So using these two isomorphisms one can get this isomorphism.